So welcome everyone to Algorithms Live. This is our episode 1. Episode 1, and this week is going to cover trees and diameters. And so this will be fairly exciting. Of course, this week we're mirroring the Donald Knuth's lecture series. He's every year he does a lecture on trees, so he learns one interesting fact about trees. And I did put a link to one of his Christmas tree lectures in the live blog, or in the blog. And you'll notice he was wearing this shirt, "Party with Trees." So I thought it was appropriate to make my own. I put a little hat on my drawing of the tree here. And so that's really what we're going to be covering today. And there's a lot I can do with trees. Here at UCF, there was one semester where I decided to give a tree lecture, and gradually it turned into another tree lecture followed by another one. I ended up spending an entire semester just talking about trees. So there's a lot I could be covering with trees, but I think this is a good starting place, and I'll try not to make this trees live, and instead algorithms live. So I'll try to mix it up each week. But that's our starting place this week. So I'll go into black mode here. So first, I think a good place to start is just defining what a tree is. If you guys remember, so what is a tree? And I'm, of course, talking about the graph theory version of tree. So we can take this first component is we have to have a connected, undirected graph. So that's the first thing. So it's got to be connected. So for every pair of nodes in the graph, you have to have some kind of path between them. There needs to be a way to get from one node to the other. And then you also need to pick one other property to be in your graph. And there's actually quite a few options because there's equivalent definitions to trees. So one option is you could say, well, there's no cycles in my tree. Right? So if it's a connected undirected graph with no cycles, then you know it's a tree. Another way you could say this is it's a connected undirected graph with n vertices, but n minus 1 edges. And that's enough to tell you that it's a tree. Another thing I could do is I could say connected undirected graph, but then it only has unique paths. Right? So if I take any two pair of nodes, there will only be one way that I can get from one node to the other by walking some kind of path. And the last one that's quite popular is remove any edge, and the graph becomes disconnected. So in other words, it's fragile. That's another way we could say this. And what's interesting is the most common one is just put these two together. That's your definition. When you're building something in mathematics, you usually just define things once. And these are all other equivalent definitions, so you can prove them equivalent. And what I actually did the first time I gave a lecture on this is I did a bunch of two-directional proofs, and I have these crazy notes where I was going in both directions. And so actually you can do all 12 directions and prove that they're equivalent. But this is kind of stupid because you can just prove some cycle and say that this is equivalent to this, is equivalent to this, or this implies this, implies this, implies this for properties on trees. And they'll all end up showing that they're all equivalent definitions, and you don't have to do more than 4 proofs. But I'll save you the trouble today. We won't go over those proofs, but you can try them yourselves. We'll go over some more interesting ones to view. And so that's what a tree is, and that's our starting place. So the main topic today is actually covering this concept of diameter. So if you're dealing with some kind of a tree, well, the diameter is actually defined more generally than just a tree. I can define it on a graph. So the way I'll define it here is the longest of shortest paths. In a graph. So give me some graph. It doesn't even matter what kind of graph it is. So in this case, I'll draw a 4-node graph that's not a tree. And as you can see, if I walk from this node over to this other node, so if I start here, and maybe this is the path I take. So give you maybe that's my path. You'll notice that's not the shortest path. So that's not what I care about in terms of diameter. So a diameter is going to be the shortest path possible, but you want to maximize it. So you want to pick a pair of nodes that are the furthest apart. So maybe if I delete this edge, you'll notice that the shortest path from 1 to 4 is now 2. And so this will have a diameter of 2 in a graph. So in general graphs, this is a bit harder. But there is a fairly simple way to do it. So for general graphs, I think the easiest way to code is first you run Floyd-Warshall's. So that's the all pair shortest path algorithm. You can look this up later if you're not familiar. So that's step 1. And then just do 2 for loops, just nested for loops, and just check all pairs and just report the max that you see. So that will be the diameter. And of course, this is going to run an n cubed because Floyd-Warshall's runs an n cubed. So that's really the bottleneck of this algorithm. But on trees, this concept of diameter gets much simpler. So on trees, it's just simply the longest path in a tree. And the reason is, it's the same definition here, but this concept of shortest path doesn't really make any more sense because a tree is composed of only unique paths. So we just get rid of this concept of shortest path and just say only unique paths. So the runtime comes down to n squared. And the reason is you just try all endpoints. So one side of the endpoint. And then run a BFS to find how far everything else is away from that endpoint. And the BFS runs in order n time due to this fact. There are only n-1 edges in the tree. But we'd like to bring that runtime down. We'd like to have an algorithm that finds a diameter in order n. So here's our problem. Our first problem we're going to try to solve is we're just going to try to find the length, just find that furthest path length. So I'll just go over really basic technique for attacking tree problems. So we've talked a little bit about trees. Let's talk about rooted trees. So we have this concept of rooted tree. And what this is a digraph where the edges orient away from the roots. So and so a digraph is just a directed graph. That's just the short name for directed graph. And we also have this technique called rooting the tree, because you'll notice a lot of trees that we deal with don't have a root. They're undirected. So it might be something like this. And so maybe I give these labels. So 5, 7, 8. And so the rooting, the tree is pick a vertex to be the root. And that's all we're going to do. So if I select, let's say 1 to be my root, then it'll look something like this. So vertex 1 is over here, so maybe it points to 2 and 3. It also points to 4. And then we have a subtree over here that's a little more complicated. And so a lot of times when you're dealing with a tree problem, one of the first things you do is you pick a root, because dealing with the rooted tree is much simpler than dealing with this undirected tree. That's not always the case, but it's probably the most common way you're going to start a tree problem if you're dealing with a tree. So I'm going to define a function we're going to precompute. So we're just going to precompute a table for this function. And it's basically just going to tell us some information about the tree that's going to be really useful for finding the diameter. So it's basically a height function. So it's going to tell us the depth, and it's going to go from a vertex to a integer greater than 0. I'll define it formally here. So its d of v is basically just going to be one of two things. It's going to be 0 if we're a leaf. So vertex v is a leaf. In other words, it has out degree of 0 if it's going down. So it's got no children, then it's a leaf. So these are all leaves that I'm circling here. The other case is I just look at all my children and I look at the max depth. So let's move this over here. So in other words, what I'll do is I'll look at this tree and I'll just look at all my children and say, what's your max value for dv? And then I'll basically add 1 to that. So if I look at this tree I have built over here on the right, this rooted tree, this function is going to just be 0 for all the leaves. And then we just add 1 to the min of those, our max of those, and then add 1 to the max of those. And it basically just tells you the height of the tree. And so a lot of tree problems just start out with some kind of precomputation. So we can precompute this just with the DFS in O of n time. So you just, on the post order side of the DFS, after you're done exploring all the children, just compute this function coming back up. So this will help us, because if we precompute this function, it'll be really easy to do our first algorithm for finding the diameter. So here's our first algorithm. The idea is first, we calculate the longest path through the root. So we assume that the root of the tree is the longest path in the tree, or is on the longest path in the tree. And then what we do is we delete the root. Because if it's not on the longest path in the tree, we can just get rid of it and say, oh yeah, it's not on that. So delete the root and then just solve the problem on the subtree. So it's kind of like a case, there's casework here. The first thing I do is I just assume that I'm on the longest path in the tree. So I'll draw out a tree here, and these little triangle things just represent subtrees. So sometimes if I'm drawing pictures, it means that there's some subtree here and I don't want to draw the whole thing out. So what I'm doing first is I'm just assuming that I'm on the root and the diameter is going through me in some way. And then if that's not the case, then I just delete that root. And then I move on. So let's go back here, move to the right. And what I'm left with are a few subtrees. Right? And the root's gone. So all I'm going to do is say, well, now these are trees. So I can just solve the problem again. And the answer is just going to be the maximum of all these results. So we basically assume that we're on the longest path. If we're not on the longest path, we can just remove ourselves. We don't actually have to physically take us out of the graph, but it will, we can just assume that it's gone and then continue on with our algorithm. So this longest path through the root, that's a subproblem that I should probably elaborate a little more on there. So let's see how we do that. Because once we get that piece, we can just solve our problem recursively by walking down the tree in a DFS fashion, and then just save the longest answer we found. So the max one through the root, here's our root, and we have a few subtrees. And we also have depth information for each of them. So maybe we know that there's the longest path down this subtree is of length 5, or maybe this one's length 3, this is length 4. Well, if we want to form a really long path, what we can do is we can stitch these two paths together. So we do that by greedily pairing the two longest paths. And so here what I'll do is I'll pair 5 with 4. So the cost is just going to be the sum of edges I use. So 5 plus 4. And then we have these two edges that get added onto our path to go through the root. So I get plus 2. I'm left with 11. And that's the length of the path. And this almost works. There's one case where this doesn't work, and that's if I only have one child. So I could have a tree like this, because I'm rooting pretty much arbitrarily. Then there's nothing down here to pair with. So it's pair the two longest paths, except the easiest way to code it is just assume that every tree has a path of length 0 from itself. And that way you don't get into a bug where this case ends up breaking you. But that's how you compute the longest path through the root. And so you just pre-compute an order n time, then you do one more DFS, and you basically just figure out how to stitch these paths together. You can also code it, I believe, just with one DFS, if that's a little easier. Not every problem you can. Sometimes you have to do the pre-comp then something else. But I believe for computing this information, you can just do it in one DFS and then be done. So that's the first algorithm for finding the diameter. The second algorithm is a little bit strange. So this is the second one we'll try. And this one is greedy. And to me, it's surprising that it works. So here's how it works. The first thing we do is we take any node. So just pick any node. So then the second step is you run a BFS from S. All right. And then from that BFS, we just find what's the furthest node from S, subject to that BFS. So what's the furthest one from S? So the BFS tells us that information. And then we run a BFS from T. And then we ask, well, what's the furthest node from T? Well, I'll say, well, that's R. All right, you do all that, and this is the answer. So the answer is r to t is a diameter. And this should really sketch you out. Like, the first time I was shown this, I was very surprised that this worked. But I couldn't come up with a counterexample, but I didn't have a good understanding of why it worked the first time I saw this. And so I'll talk to people every now and again about this particular algorithm, and they'll be like, oh yeah, this totally works. It was obvious to me. And so what I would do, I'm going to ask you some questions here, and I'm not going to tell you the answers. I want you to try to figure it out on your own before we go into why this one works. So if I run the same algorithm, does it work on an almost tree? And so I'll define what that is in a second. So there's a special type of almost tree, and I like to call it a Cthulhu graph. And the reason I call it that is there's a topcoder problem, or no, it's a code forces problem about Cthulhu graphs. And it's basically talking about this special type of almost tree. So I'll define what an almost tree is here. If you want an almost tree, what you do is you draw a tree, or in this case, a Cthulhu graph. You just draw any tree like this. Doesn't matter what kind of tree it is. And then you just add a single edge to that tree. So it's a connected undirected graph with n edges for n nodes. And that's an almost tree. So you could ask yourself, does this algorithm too, for finding the diameter of a tree, does that work on an almost tree? Does that work, yes or no? And then another question you can ask yourself is, does this work on general graphs? And I'm not going to tell you the answer. And you can debate amongst yourselves why you think this would work. But I'll present the proof for the tree case, at least. And that should be fairly interesting. So here's the proof of the tree case. So there's two cases, right? Basically, there's two ways I can break this up. When I've picked an arbitrary S, there are two options for S. One option is S is on the diameter. That's option one. So if it's on the diameter, I want to know what that first BFS gets me. And it turns out the first BFS gets me something that is the endpoint of the diameter. And we know this by algorithm 1. So if I look at algorithm 1 and I run my BFS, T is going to be an endpoint of the diameter. Right? So if I found an endpoint of the diameter, if I run a BFS from there, of course, I'm going to find the shortest path from that particular node. So in this case, if my starting node just happened to be on the diameter, then I'll surely find the diameter of the graph by running a BFS twice. But then there's also this case where S is not on the diameter. And that's a little more problematic. So here's S. And if we're running our BFS, what you're going to notice here is we basically just have to prove that the diameter is always down the deepest subtree. So if I have some subtrees, C1, C2, and C3, and I'm sorting them by depth, I'm going to run a BFS down this way. And this might be my diameter right here. If S isn't on the diameter, it might just be this path from here to here. And the depths are increasing. So this depth is bigger than this depth and so on. And so what I'm going to say is I have property I. So I'll call this property I. And what this basically says is C1 contains a diameter. So in other words, if I'm in my tree and I know that I'm not the diameter, so I have to know that I'm not on the diameter of the subtree, then the thing I want to prove is my deepest subtree is going to have the diameter. And if I prove this property I, then you'll know that I've basically proved that my second algorithm is correct, because what will happen is it's basically an inductive argument. Here's the basis step. The basis step is if I'm on the diameter, then I'm definitely finding the endpoint of my diameter. But if I'm not on the diameter, then my diameter is going to be down the deepest subtree, or there will be a diameter down the deepest subtree. And that's what this property I is. So what will happen is this argument works in an inductive way. I start at whatever node I am. I go down to the deepest subtree. From there, this property still holds. I go down to the deepest subtree until eventually I hit the node that's on the diameter. And then I'll definitely find the endpoint from there by going down the deepest subtree. So that first BFS is definitely going to find an endpoint of my diameter if this property I is true. So that's why we want to prove property I. And that's all we need to prove is property I is true. And that's what I'm going to do here is I'm just going to prove that by contradiction. Because proving that will prove that my algorithm works. And so here's how this works. So the first thing I'm going to do is I'm just going to assume the opposite. I'm going to say that suppose that C1 does not contain the diameter. And then we're going to have a problem. So here's how this is going to work. Here's the root of my tree. Here's C1. It's got whatever its depth is, it's got some path of that depth. So D1 is equal to D of C1. So I'll call this length here D1. And we'll say it doesn't contain the diameter, so there has to be some other tree, C of I, that does contain the diameter. And in the worst case, it's going to have two paths of length D2. So they might not be the same length, but it doesn't change anything in the proof if I make them the same length, and it ends up being the same distance. So you could work this. It'll muck up the proof a little bit, but you could work this if they're different lengths, and I'll leave that to you all. So here's the diameter going through some other subtree. I don't know what this other subtree is. That's why I'm calling it CI. But I happen to know the length of its diameter. It's 2 times D2, because it's the path length from this node to CI, and then from this node to CI. And I'm just stitching that path together. And I get that. And what I'm going to show for my contradiction, because I have to show that something goes wrong if you assume that C1 doesn't contain the diameter, something else contains the diameter instead, I'm going to show that I can form a longer path length. And that's going to contradict that this is the diameter. by forming a longer path length. So here's how I'm going to form that longer path length. I'm going to take this path length, which is D1. So I have D1. And I'm going to stitch it with the longer end of CI's path length. So this is D2. And of course, I have to add on these two edges. So plus 2. But I also know that D1 is greater than or equal to D2. Because this is the deepest subtree. C1 is the deepest subtree. So that's why I get this inequality right here. All right, so if you're dealing with inequalities, a lot of times if I'm doing algebra, I don't really want to deal with the inequality. So what I can do is I can rework it, and I can say that this is D1 is equal to D2 plus some delta, where my delta is greater than or equal to 0. And I'm going from an inequality to an equality, and it makes it easier to manipulate things. So that's what I'll do here. I'll just substitute D1 for D2. And so I'll end up getting D2 plus delta plus D2 plus 2 is equal to 2D2. So I'm adding these two things and putting them together, plus delta plus 2. And so what you realize is this is a positive integer. It's going to be greater than or equal to 2 because this is greater than or equal to 0. So I have some residual left over. So I know that's definitely strictly greater than 2D2. So in other words, this path that I built is strictly greater than the diameter. And I said that this was the diameter, so clearly I have a contradiction. And I just prove that it must be down my deepest subtree. So life is good. All right, so now we know we have two methods for finding the diameter. We can do this 2DFS method where I basically run a BFS from some node to some other node, and then run a BFS from that node to that other node. Or I could do this DFS method where I pre-compute some information, find that information. Here's a fun problem that you guys can work on while you're working through this lecture. Is I keep calling it a diameter. So how many diameters can there be? So if you could form a tree with n nodes, how many diameters can you have? Like in the worst case. And then the other question I'll ask you is, maybe come up with an algorithm so you can count the number of diameters in T. So I give you some tree, and what you want to know is how many diameters are there? Because there can actually be more than one. And so these are two questions you can ask yourself and see if you can figure out the answer. And at the very end, I'll give you the solution. So something for you all to think about. And that's one thing we can do. So I'll define a new property on trees. So we have this property center that exists on trees. But before I define that property, I need to define some other term. So I'll define this term remoteness that'll help me define what a center is. So if I have some vertex v, v's remoteness is just its distance from its furthest node. All right, so once again, it's just a function. You pass in some vertex, you get some integer that's greater than or equal to 0. So non-negative. So if I draw out a graph like this, I could define what remoteness means. So you can kind of just see how this function goes. so this node right here has remoteness of 4 because the furthest node from it is this node right here, and it uses up 4 edges to get there. So we have 1, 2, 3, 4. Yikes. Consequently, this has remoteness of 3. Same node as the furthest one away. Same thing here. This is remoteness of 3 as well. This has remoteness of 2. This has remoteness of 3. This node is the furthest one away, and it's 3 edges away. This has remoteness of 4 and remoteness of 4. So we have this notion of remoteness. And what we're going to do now is use remoteness to define what a center is. So center in a tree is a node that minimizes remoteness. So that one. That's going to be my center of my tree. So this node with remoteness of 2 is the center of my tree. And there can actually be multiple centers. So if I draw a different tree, I have remoteness of 2 here, 2, 3, 3, 3, 3. And so you'll see there's a tie. So those two nodes have the same remoteness. So how do we find the center? I think the easiest way is a lot like a topological sort. So you just pass in some tree like so. And the first thing I'm going to do is I'm going to take all the leaves and I'm going to just delete them. So anything that's a leaf, I delete it conceptually. It goes away. What I'm left with is the tree that remains. So then I delete the leaves on this tree until I get down to a single node or pair of nodes. So I can just continually delete things, and that's what my center will be. So I'm basically just collapsing the graph inward until I find what the center is. But centers have some interesting properties. So that's probably what we want to talk about with respect to centers. And so here's my first theorem on a center. So let's say I have a tree. And let's say I have a center. So there can be multiple centers, but I'm just picking any center. And the theorem goes something like this. It's all diameters in T must go through the center. And since this is an arbitrary center, it's basically saying it must go through all centers. So it doesn't even matter which center it is. It has to go through all the centers. And so I'll prove that real quick, because this is also pretty interesting. So you can have multiple centers, but all diameters must go through them. So the proof looks something like this. Once again, I'll use proof by contradiction. So I assume the opposite. I assume that the diameter doesn't go through C. And to make this proof easier, what I'm going to do is I'm just going to root my tree at the center. So there's my center C, and I have a bunch of subtrees hanging off of various kinds. And what I'm going to assume is that there is some diameter that doesn't go through my center. It might go through some other center potentially. So I know some things. I know that if I put these in increasing order of depth, that my diameter, so maybe this is D1, and this is the second deepest node, this is D2, then I know exactly how big my diameter is. It's going to be 2 plus D1 plus D2, because I have to add that one node coming off those subtrees. And that ends up being my diameter. And I also know that the maximum size a diameter in another subtree could be is going to be, so if I have my diameter, its size is at most 2 times D1. So what I'd like to be able to do, and I also know that D1 is greater than or equal to D2. That's another fact that's useful. So what I'd like to be able to do is find some contradiction here, saying that, oh yeah, if I have another diameter in some other subtree, so maybe there's a second diameter that pairs D1 with D1, that it could potentially not go through C. And we're going to find that there's actually a problem here. But it's not going to be the same problem we saw in the previous proof by contradiction. You can't really construct a path that goes through, show that D1 to D1 isn't part of the diameter. Like, it's not possible to have something of this length in that subtree. That's not as easy to do, because D1 could be it could be smaller than D2 can be smaller than D1, so that these facts that we have right here aren't good enough at the moment to prove that we have a problem. So what I'm going to do is I'll add one extra fact about D2 that is going to be useful. And that's, it has to be greater than or equal to D1 minus 1. So D1 and D2, these two lengths over here, can vary by at most 1. And you can prove that by contradiction. You can basically assume that D2 is less than D1 minus 1. And then what you'll find is you'll actually show that C isn't a center anymore, if that's the case, because you'll find something with smaller remoteness. So I'll let you work that out if you'd like to do that proof. But now with this extra fact, it'll be really easy for us to see an issue. So I'll do this by cases. So I'll work out both cases, and you can see how this proof works. So the first case is D1 is equal to D2. And it's basically, each case is almost the same, but I'm working them out differently. So if I take, what I'm going to show is the diameter is strictly greater than the maximum size that a diameter in some other subtree would be. So it has to go through C. So I have D, and that's equal to D1 plus D2 plus 2, which I can just substitute for D2 with D1. So I'll end up with 2 plus 2 times D1, which I happen to know is greater than 2 times D1. So my diameter is bigger than anything I can make in that subtree. So it's obvious that there's no diameter not going through C in that case. And then my second case is D1, D2, I should say, is equal to D1 minus 1, because that's the other case in this inequality. And it just turns into the same proof again almost. So you get D1 plus D2 plus 2. And then I substitute for D2. I get D1 plus D1 minus 1 plus 2, which is 2 times D1 plus 1. And I have this residual plus 1. So that's greater than 2D. And so I've basically shown that in either case, you can't form the longest path you can form in some other subtree, not going through the center, is strictly less than what I know to be my diameter. And so that's a contradiction in either case. And so it completes our proof that this property holds. So it has to go through the center, which is useful to know. So there's another property that's also useful on centers. And that's that there are most two centers in any tree. And for the proof, I'm just going to leave that up to you guys. You can try this one. I won't do that one. It's not terribly hard, so I'll leave that to you all. All right, so that's what I have for centers, and I'd like to go over one more property of trees before I go back to that counting problem that I mentioned earlier. So the next property is I want to talk about centroids in trees. And so for those of you that are interested in centroid decomposition, first learning about centroids is useful. So or divide and conquer on trees. Then just knowing what a centroid is and knowing a few of its properties will help you understand that. So here's how we define a centroid. So let's say we take a graph like this. And what I'm going to do is I'm just going to delete some node in this tree. So it disconnects the graph. And that's going to help us define centroid. So a centroid is a node, when removed, maximizes the largest remaining component, or minimizes, sorry. So what I'm left with is whatever size that is. So if I deleted this node, for example, my remaining component would be 1, 2, 3, 4, 5 nodes. Or if I delete this node that I chose to delete, my largest remaining component would be 3, which is much smaller. So for a centroid, I'd like to find basically that place to split. So a good question to ask yourself about centroids is a centroid always the center? So you can think about that. I'll give you the answer here. You can draw a graph. Maybe one more node. Yeah. And then what I could start doing is putting a lot of nodes off of one of these nodes. So you can see that this is my center, but my centroid is going to be over here. Because if I remove that node, this is the only component that remains. But if I remove the center, then I've got this huge component over here that remains. So this is the centroid, but the center over here, if I do that algorithm where I restrict that graph and I minimize remoteness, this node minimizes remoteness, where this node minimizes the maximum component that's left after I remove it. So let's talk about how you find a centroid. So once again, I'm going to create a function from each vertex to a non-negative integer. And what this is a subtree size function. And I'm going to define it this way. So if I have some vertex v, then it's going to be one of two things. It's going to be 1 if I have a leaf, or it's going to be 1 plus I look at all my children and I sum together their s values. So this is the case where I'm not a leaf. So I'll give you an example of what that looks like. I could have a tree like this. And I can just pre-compute this with DFS. So all the leaf nodes are going to be size 1, and then I add my 1 node to that node. So if I have a rooted tree, this function exists on a rooted tree, not a regular tree. So I have to root the tree somewhere to do this. But I could do this node here. That's going to be size 3, and this one is size 10. And so once again, I can pre-compute this in O of n time just by doing a DFS, and on the way back, I just save these subtree aggregates. So I'm really just saving information on my subtree as aggregate information. And pre-computing this, so in this case, I actually have to pre-compute it before I run the algorithm again. But first, I pre-compute the subtree information. And then I can use it to find the centroid. I think I could still run it in one DFS, but you can figure out implementation details. So if I'm at some node in the tree, I know exactly for each of its children, these are going to be components when I remove that node. But one scary thing you have to realize is there could be an edge above me, and there could be trees hanging off here, and there could be edges above that with trees hanging off here. So I know if I'm at this vertex v, if I delete this vertex, this will be a component, this will be a component, this will be a component. But this crazy thing right here is also going to be a component. And I need to know the size of each of these components that remain when I remove this vertex v. So these follow very naturally from that function because it's just going to be s of v. But this one above me, so essentially I have a parent tree that's coming out above me, and then I have all my children. Well, that parent tree can be computed very easily. What I do is I take my current subtree and I subtract it from n. So if I do n minus s of v, then that's going to give me the parent edge size. So it's going to give me this piece up here above me. And so this is an example of inclusion-exclusion. I take all the nodes and I subtract out my subtree, and then I know how big everything above me is. So it's really not that bad to compute. So now I have, it'll be really easy to run an algorithm to find the centroid. The first thing is I try all nodes v. And then for each of them, I just compute the largest remaining subtree. And then the answer is just going to be the min over all these. So whenever I find the node that its removal causes each of the maximum subtree that remains to be as small as possible, that's the centroid. And I can have multiple centroids, but a lot of times I just need to find one. But centroid also has a few useful properties. So here are some properties of centroids. So the first one's very similar to trees. So there's at most 2 centroids. And the second one is if you remove the centroid, you actually have some information on the subtree that remains. So the subtree goes away. So if I have an n node tree, my component is going to be at most half the size of my original tree after I remove that, which is a good observation because this is great for divide and conquer. So if you think of binary search, you want to cut the sequence in half at every single stage. Well, in this case, I'm basically cutting my tree and at most half. I could cut it into a bunch more pieces, but each of those pieces are going to be at most half size, which is one of the reasons why divide and conquer on trees or centroid decomposition trees have that logarithm depth, which is when you remove the centroid, the remaining graph is going to be cut in half essentially. So that's exciting. And so that's what a centroid is. All right. So the very last thing I'd like to do now is I'd like to go back to this counting problem and count the number of subtrees that are, count the number of diameters in a tree. So hopefully you maybe gave a little bit of thought to this problem, but if you haven't, you could pause the video and try to figure it out yourself because this is a fun problem to work out. But count the number of diameters in a given tree. So the first question I asked you is how many diameters could there be in the worst case? So if you were to construct any graph, what's the maximum number of diameters you can make if you could make any tree? And you should have come up with something like this, a sort of wheel graph. And you'll notice this has a large number of diameters. I pick any pair of nodes, and that's going to be a diameter on this outside circle. I can't pick the center node, but any pairing otherwise will work. And such a graph is going to have n-1 choose 2 diameters. And this is useful information to consider because if you're trying to code a problem like this, if there are 10 to the 5th integers, if there are up to 10 to the 5th nodes in the graph, then this is going to be around n squared. So it's going to be around 10 to the 10th in size, which overflows an int. So you have to use a long if you were to work a problem like this. But the problem I gave you was given some tree, count the number of diameters that exist in that tree. And what we're going to do is we're going to use those 2 facts we proved about centers of trees. The first fact we knew is that there are most 2 centers. The second fact we knew was every diameter has to go through the center. So if we work from the centers, it's actually really advantageous. So I'll work the two cases separately. So the first case, so this is my case 1, is the case where I have just one center. Now let's see how we can compute how many diameters are in that tree. So I'll root the tree at the center. So first I have to find the center, but we already know an algorithm for doing that. You can also do it with DFS while you're finding the diameter. There's multiple ways to find the center, so you don't have to use just the first one I recommended. And I'm also going to compute some information here. I'm going to compute this information SI. And what this is the number of nodes, depth d divided by 2. And the reason is I'm going to pair the two deepest subtrees together to form a diameter, because they have to go through C. So I might take some node down this subtree and pair it with some node down this subtree, or some node down this subtree and pair it with some node down this subtree, and so on. So I could have some weird pairings going on like that. I'll give you another example. So let's say I drew a tree like this. Then this node is going to be the center. And so I write out, if I root it, it's going to look like this. So if I look at this subtree, there are at most 2 nodes that are at half the depth away. These 2 nodes. If I look at this subtree, there's 1 node that's half the depth away. And these 2 remaining subtrees, well, there's 0 nodes with half the depth away. So the number of diameters in this tree is going to be 2 times 1, because I pair everything from here with everything from here. And that would tell me the number of diameters. So there's at most 2 diameters in this tree. There's this diameter, and there's this diameter. But if I want to do the algorithm more generally, I can compute these SI information for each subtree. And now I'm basically solving a problem on a sequence. I'd like to go to a specific subtree, so whatever subtree I'm on, and I just consider pairing it with everything that's behind me. So I consider pairing S3, all of the nodes that are depth d minus 2 in this subtree, with the ones in S2 and the ones in S1. So what I'll be doing is I'll be keeping a running sum of everything that's behind me, all the nodes that are maximum depth, essentially, in each of the subtrees behind me, and pair them with the current node that's there. So I can write this out formulaically. I can say the sum up to and including that position is the summation from I equals 1 to n. And all I do is I take SI and I multiply it by the sum of the pieces in front of me. Sj. And so I pair these two things together, and I can compute this with a running sum. I don't actually have to run that for loop every time so that it's fast. And that's the number of diameters in this tree. So that's case 1. Case 2 is a little easier. That's the 2 centers case. So I have 2 centers here. I have C1 and C2. And I have some subtrees hanging off. Maybe something like that. And then I could have 2 centers with these subtrees hanging off. Something like that. And if I take everything of max depth over here, I can pair it with everything of max depth over here, because remember, all diameters have to go through both these centers. We proved that earlier in the episode. So my answer is just going to be the number of max depth. So imagine I cut this edge, for example. So maybe I'll use a different color. So it's the number of max depth in C1 times the number of max depth in C2. And that's my answer for case 2. So I'll open it up for questions. If anyone has any questions, write them in the chat. And so while I wait for a few questions, I'll preview next week. Next week's for Algorithms Live, we'll actually have our first guest. We're going to be talking about a pretty hard problem. And so it's exciting because he's got some interesting bounding methods that I haven't been exposed to before. So I'll be learning some stuff. And then I'll be going over an alternative. We're going to be talking about one problem the entire episode. And I'll be going over an alternative solution to that problem that's also quite interesting. So it should be a really interesting episode. And I hope you all will enjoy that. It will be our first guest, so it'll be more than just me talking next week. So we'll have, and I'll announce that guest later in the week. And check the blog. It might be at a different time. We haven't discussed exactly what his availability is, but I'm excited to have our first guest. And I hope you all will enjoy future weeks of this, and I'll see you all next week.